Okay, we'd like to thank you for meeting with us today. We are going to be talking about how to electrically supply electricity to Las Vegas. We would like to thank Dr. Hendengren, specialist in optimization and process control, as well as Dr. Baxter, expert in energy engineering here at BYU, for their help in our optimization project. We had a few concerns starting this project as far as meeting electricity demand as well when we're using renewable resources, and we wanted to combine renewable resources with non-renewable resources in order to meet peak and base electricity demand. The goal was to do this without brownouts and to not overproduce in order to decrease costs for the company. So we'd like to start our presentation now. As far as our system parameters, we needed to define exactly what was the scope of our project. Essentially, we defined that natural gas was going to be our main electrical supply, followed by nuclear and then coal. And these plants would essentially have a given ramp rate. So they could be able to ramp up given a different demand difference, and they would ramp up a certain percentage of their plant capacity per minute in order to meet the demand. So a little bit about how our system worked. So first we defined a demand based on tabulated data online, and we fit that model to fit the Las Vegas electrical supply, and then we introduced a disturbance with a time delay in order to simulate a fluctuating electricity demand. Then we also looked at solar and wind. In order to model our solar and electricity, we used a couple of ramps in order to ramp up in the morning at sunrise, level off during the peak hours of the day, and then ramp down at sunset. And then we had our wind power was a constant 75 megawatt capacity with large disturbances in order to model the intermittent wind power supplied.
Right here is the sort of brains of the project. This is where our controllers are, and each of the three lines there represents each of our plants, so nuclear, natural gas, and coal. We told each of the plants to overproduce by 50 megawatts in order to give ourselves a little buffer in order to reduce brownouts. And the PI controller then takes the demand difference and tells each of the plants to ramp up or ramp down. But one thing that's different about this model compared to the normal models that we do is instead of using an FOPDT, we decided to use a ramp. And this simulates a plant better because it has a maximum ramp rate on it. And so the plants can't ramp up faster than would be normally feasible. There's also a time delay on there because from the time you want the plant to ramp up and the time it actually ramps up, it's not instantaneous. And so one of the parts that we implemented in this system that's, I think, the most innovative part is that this section is a battery or a large-scale energy storage device. And this guy accumulates that overproduction that our plants are doing. It's accumulating that and then is able to discharge when we need it to. And the way it works is the limited integrator accumulates that energy up to 400 megawatts, and so that's the capacity of our storage. And so we're talking large-scale storage here. And then the PI controller is allowed to discharge that energy whenever the battery is charged in order to meet those sharp peaks in demand. Our plants weren't able to meet those peaks because of their slow ramp rates, and so by implementing the battery we were able to meet very sharp peaks because the battery is almost instantaneous. You can see from the graph, it's a little small on here, but the green oscillating line was our supply, our system without the battery. And then there's also a red line that you can see when we implement the battery, all else being the same, it smooths out a lot. And so the battery increases our stability by quite a bit there. And also it reduces our brownouts. We actually didn't have any brownouts with the implementation of a battery of this size.
So for stability and tuning, first before we could tune our controllers, we conducted a stability analysis, but it was determined that we only needed to for the natural gas controller because of the capacity, the lower capacity and slower ramp rates of the coal and nuclear plants. They ultimately couldn't make the system unstable. So we conducted the stability analysis and determined that the P-only controller for a natural gas needed to be between negative 1.95 and positive 9.34. So we tuned all of the controllers under the criteria of minimizing overshoot and completely eliminating brownouts. And we were able to do that with a Kc of 5 and a tau of 0.5 for each controller. So in conclusion, we were able to design and tune this control system that was able to meet sharp peaks in demand and be able to balance the production of energy from renewable and non-renewable energy sources with a large-scale energy storage system that was able to have tight control over the demand curve and be able to meet a demand curve of any shape or size.